In this video, I'm going to show you how to use an audio analyzer, and in this case, the Quantasylum QA403 audio analyzer you can see on the right-hand side, to analyze a typical audio system. When we're talking about audio analyzers, this is typically measuring things such as signal-to-noise ratio, total harmonic distortion plus noise, noise floors, frequency responses, and so on. The reason we might want to do this is because you might want to add this to a spec sheet. If you're, for example, looking to buy an amplifier or headphone amplifier, these are specs that are commonly listed. The system we're going to be analyzing is the custom PCB you're seeing on the left-hand side, which is a custom digital guitar effects processing platform. It features an STM32H7 microcontroller, which interfaces with an audio codec, which contains ADCs and DACs, and that has its own analog front end for mono in and mono out. So I can take a guitar input and feed it onto an amplifier and do some effects processing on the STM32H7 microcontroller. We'll go into the hardware in a tiny bit more detail because we'll need to know a few things before we can do some audio analysis using this QA403 audio analyzer. Hopefully this video will be useful to show you certain measurement techniques, what to pay attention to when using audio analyzers, and also of course a walkthrough and demo of the QA403 by Quantasylum. The guys at Quantasylum were very kind and sent me one of these QA403s to try it for myself, and I've been using it also for my main work quite a bit, and therefore I'd like to also show you this in this video. Compared to other audio analyzers, for example from those from Audio Precision and so on, these are very, very inexpensive at only a couple $100 or euros. The QA403 is completely USB powered, provides pretty amazing specs at minus 110 dB THD+N, so total harmonic distortion plus noise, various input and output voltage ranges. It's completely differential input, completely differential output, features a pretty easy to use software, which I'll go through in this video, and more. I'll leave links to this in the description below so you can check out the specs in your own time. If you'd like to learn more about audio analyzers in general and what they're used for and differences between audio analyzers, I'll leave this wiki link in the description below, which goes to the history, how they typically work, and what you can do with them, although we will be seeing that in this video, of course, as well. A huge thank you to PCBWay for sponsoring this video. The PCBs we're going to be analyzing in this video were manufactured and assembled by PCBWay in China, and they've turned out absolutely great, and I can highly recommend their services. You can of course just get blank PCBs, but they also offer PCB assembly, as well as flex PCBs and rigid flex, as well as many other advanced options. And I'll leave a link to them in the description box below. If you'd like to get some mixed signal hardware design tips and have a bit of an insight into this hardware, make sure to check out video number 88 on my channel, which goes through exactly that. Additionally, another PCB that was manufactured and assembled by PCBWay you can see in video number 78, which goes through the entire design walkthrough of a custom rather small mixed signal PCB, which features very similar STM32H7 microcontrollers, as well as the same codec we're using in this video. The hardware itself is pretty straightforward. It's a 4-layer PCB, components top and bottom. Effectively, I have a 1/4-inch jack on the input, where I effectively can plug a guitar in, for example. That gets fed through an analog front end, effectively just a couple of op amps, filters, and so on to set the upper and lower cutoff frequencies, provide some impedance conversion, and so forth. That feeds into this codec, which is a Cirrus Logic CS4270. And then we have an I2S stream that feeds effectively the STM32H7. We can do some processing on board, and then again an I2S stream that feeds out again to the codec DACs, through an analog front end, filters, buffers, and so forth, and that gets sent to the output jack, which is again just a 1/4-inch jack, which could go, for example, to an amplifier. I do also have these 2 foot switches. The one on the left is actually a true bypass control, so I can completely bypass any of this digital system and any of the buffers, so I get a straight feed from input to output. And this right switch is just effectively a toggle switch connected to a GPIO pin of the STM32H7 microcontroller. There are other, of course, control interfaces, USB, power inputs, and so forth, as well as a programming header. In terms of firmware, we want to keep this very, very simple. So we want to analyze the system without any effects processing going on. Effectively, this is just an I2S feed through. So we take in the data via an I2S stream, we do pretty much no processing, and then we just send it out back to the DAC, because we want to measure the baseline, for example, noise performance, distortion performance, maximum signal levels, and so on. So in the project that I'm loading onto my STM32H7 microcontroller, I have defined that I'm running at a sample rate of approximately 48 kHz, and I'm using a 16-bit bit depth configured for the codec. Of course, changing these sample rates and changing the bit depths could improve or decrease the performance of the overall system. I have my processing callback, so I'm doing my I2S, from configuring my I2S feed, so to speak, via DMA, and all I'm doing is looping through the audio buffer that I received from the ADCs, and effectively just sending them out pretty much unchanged to the DACs. There's a tiny bit of conversion between ints and floats going on, because that's pretty much going to happen in any of my audio processing algorithms, and I want to have that as my baseline. So the pretty much minimum amount of processing, just some conversions, but then sending out the ADC data straight out to the DAC. I'm pretty much doing nothing else. So this is the code that I'm now going to upload to the STM3287 microcontroller. I'm powering this device using an isolated power supply, so a typical guitar pedal power supply, which is normally at 9 volts, and then I have some onboard regulators which step that down to the required voltages on the board. The 1/4-inch jacks you're seeing here, I've actually trimmed the ends and I'm attaching these simple alligator clip scope probes, which then interface with the QuantAsylum QA403 audio analyzer. The QA403 audio analyzer is actually fully isolated and it's also differential. So the output, I'm simply taking one of the differential outputs as a single-ended, and on the input side, I am using these BNC shorting plugs to short the unused channels of the inputs. So I'm simply effectively converting the system from differential to single-ended because my audio system is single-ended. But of course, if you have a differential system, you can use the QA403 to test differential systems. I'll be using the QA40x software, which is used to interface with a QA403 audio analyzer or some of their other audio analyzers as well. This is free software. With that installed, typically what is displayed is some sort of magnitude versus frequency as our basic window. On the left-hand side, we have a few controls. Let's just go through them briefly before we start our testing. We can run, of course, our system or stop our system. We can change the sample rate of our system, so anywhere down to 48 kilohertz, but I'll be running at 192 kilohertz. There's also some other interfaces you can choose. For example, you can monitor I2S streams and so on, but for now, we won't be using this. The QA403 also contains various attenuators, so depending on the signal levels you're looking at, you don't want to saturate or get close to saturation of the front ends, because that'll increase the distortion, might decrease the noise performance, so you have to change the full scale input attenuator depending on what signal levels you're looking at. If we hover over some of these controls, quite nicely the software will tell us and give us a few hints of how we can adjust them best. Then we can also change the display, so if we want to look at the time domain or frequency domain, look at inputs or outputs, left and right channels. We can change the scales of the axes, so if we're looking at dBV, and it also tells us about the units here, or relative measurements and so on, linear or logarithmic scales, we can change the y-axes and so on. In terms of acquisition, this is effectively an FFT-based system. We can change the length of the FFT, and we can change how many averages we do per FFT. Quite nicely for audio as well, we have different weighting functions, and we'll get into that a tiny bit more later on when we do measurements. And we can, of course, because we're doing FFTs, change the window type depending on our requirements. And again, we can hover over the type of window, and it'll tell us when we might want to use these different types of windows. Once we want to perform our measurements, we can also add in, for example, markers, and we can also add in nominal measurements. So we can add in, for example, if you click on gain, we can then measure the gain, the RMS voltage, total harmonic distortion, and so on. And we can also at the top right click and add in measurements by clicking these checkboxes. And this will be very useful later on for this system to automatically calculate various parameters for us. In terms of measurements, we can, for example, use sine wave generators, single or dual channel, change the amplitude, change the frequency. We have multi-tone generators, white noise generators, as well as we can also measure the frequency response. We can add cursors as usual and so forth. So actually quite a simple bit of software, but this allows us to perform the main measurements. What we'll be seeing a lot is, for example, RMS quantities, maybe peak, peak to peak, and so on. So it's important to understand what these mean. Effectively, when we're looking at sinusoidal type signals or AC signals, rather than taking average, we typically look at an RMS, so a root means squared average, so to speak. If we take, for example, an average of this sinusoidal signal, that'll simply be 0 because we have equal areas, so to speak, above 0 and below 0, so effectively those areas cancel out. So we need a different method to calculate an average, and that's root means squared. I'll leave some links in the description below. For a sine wave, we can convert between, for example, a peak voltage or peak to peak voltage to RMS with some simple formulas. So typically dividing by root 2 for the peak value to get RMS. But for arbitrary, effectively AC signals, we basically have to do an integral in continuous time or in discrete time, a sum, take the squares, take the average, and then take the square root, very simply speaking. But nicely enough, the software, of course, does this for us, but we do need to know how to convert between various quantities. This is also true, for example, if we're looking at or faced with dBu or dBV or even dBm. dBV is effectively a logarithmic quantity, a decibel quantity, which relates the measurement to 1 volt RMS. So if we have 1 volt RMS signal, we apply this formula 20 times log VRMS divided by 1, we have 0 dBV out. So this is effectively relative scale or conversion compared to 1 volt RMS, whereas dBu is our RMS signal relative to 0.775. And we can see this is irrespective of what impedance this is measured across, whereas dBm defines also a specific 600 ohm impedance in the audio case. We will be seeing dBV predominantly and dBu. Just keep in mind these are relative quantities, either relative to 1 volt RMS or 0.775 volts RMS. There are, of course, various calculators you can use. For example, if we type in 1 volt RMS, we can see that's 0 dBV, or that's 2.2 dBu, and these are calculators we can use, or just use the tools that are in the software as well. The first measurement I would like to make is that of our noise floor. I'll leave some links in the description below so you can check out in more detail what noise floor means and why this is important. But what I like to do is measure 2 scenarios of noise floor. Remember, in our hardware, we have this 1 foot switch on the left-hand side that is effectively a true bypass. So with true bypass engaged, all I'm doing is simply routing my in jack straight to the output. Pretty much no interference of the electronics on this board, other than, of course, maybe crosstalk and the traces running through this. But that's the first measurement we want to make. Then we toggle this foot switch and we don't get a true bypass. That is our in jack is routed through the analog front ends, goes through the codec into the STM32H7 microcontroller. We do a tiny bit of conversion, send the data out again to the codec through the front end and to the output jack. So we measure once as a baseline, so to speak, and then once with our I2S feed-through system engaged to see what our absolute minimum noise floor performance is. This is, of course, limited by the analog front end. That will add some noise. It's limited by the codec we're using, our conversions in the system, and these all add together to form our noise floor. Effectively, the noise floor is the average level of all the noise sources combined in the system, again, due to the front ends, codecs, processing, and so on, without any input signal applied. Effectively, the input is grounded. We measure the average signal at the output. And then we might get a trace, something like this. So we see we have some seemingly random fluctuations, but we have this sort of average trend, and this is effectively our minimum noise level. For audio systems, there are certain noise floors we might want to achieve, and we might want to stay below and have targets, for example. For example, if we look at popular audio companies such as Rupert Neve Designs or Neve and go to one of their headphone amplifiers, look at the specs, you can see they typically have specs listed also for noise. They might have a typical load connected and they're measuring across a certain bandwidth with no input signal, so the input grounded. They're going to be measuring the output voltage across time and then averaging that. And that's typically an RMS value. So what I'm doing in my case, I'm actually now leaving for this measurement the input jack unplugged. And this is actually a switch jack. So if I leave the input jack unplugged, the input is grounded by the mechanical terminals of the jack itself. We are feeding our system through the front ends, codec, STM32H7, codec, front end, and then the output we are taking with this 1/4-inch jack that is feeding the input channel of the QA403. Now, going to the QA403 software, this is with true bypass engaged, so we're actually not doing the I2S feed-through. This is just measuring the noise floor of the system, the cables, and so on. So if I click Run, we have a 192 kHz sample rate, and my full-scale input is at 0 dBV because we don't want any attenuation because we're measuring very, very, very small signals indeed. As time progresses, we can see in the bottom left-hand side, the device is doing these bursts of streams. So it's gathering data, sending it via USB to the PC, and we're getting our noise floor here in true bypass mode. I can add measurements, of course, so I can right-click or click at the top to add measurements. We're looking at the left channel, and what we want to look for is RMS. So we can look at that, for example, in dBV. Remember, for example, typically this might be given in dBV or dBu, but we also want to look at the RMS volts and click on those and click OK. And we can see the measurements are being calculated for us. So effectively, this is the noise floor, these average measurements. Now, something you've probably already noticed is that we have this spike here, which is seemingly at 50 Hertz. I live in Europe, so this is the mains frequency we have here, which we see poking through. This is because I'm using an isolated power supply and I'm using an isolated audio analyzer. The problem with this is that we don't have a common ground or common reference, and therefore we might get leakage, such as this mains leakage we're seeing here. The way to do that is, for example, tie your system to a common ground point. So, for example, I could now take a USB connector where the shield is typically grounded and then touch that to the strip I have on the outside of my board, which is grounded on my PCB, which effectively is connected to mains ground as well. ultimately. So if I do that, and we can see this main spike is now dropping because we now have to find a common reference between all of our systems. And this is how we can then eliminate this effectively measurement error, which is this feed through of the mains 50 Hz frequency in our case. And just like that, we can now measure the true bypass or the nominal baseline noise floor. So again, input grounded, we have a common reference, and we're just simply looking at the output and measuring the RMS voltage, so the average amplitude across this frequency band. So from 20 Hz to about 20 kilohertz is the measurement bandwidth of this device. And we can see that's about 1.3 microvolts or about minus 118 dBV, which is very good. And that's, of course, due to the fact that this QA403 audio analyzer has very good performance in itself. So what I'd like to do now is I'm going to flip this true bypass switch, and now we'll engage the I2S feed through. So now I've flicked the switch and we can see we have a bit of change. Of course, we have quite a long FFT. We have a few system averages, so it's going to take a bit to settle. But what we can see now is, of course, we have a significantly elevated noise floor because of the front ends, codecs, tiny bit of processing and so on, but still a fairly okay value of about 30 microvolts on average RMS. We can see the frequency response of this noise is also not flat, so we have a bit of a boost, so to speak, in the lower frequency bands, but still minus 90 dBV might be okay for a guitar system. Keep in mind, however, also we're testing this without any load to the output, so a pretty high impedance output load, whereas you might be wanting to measure noise with typical loads connected, for example, or typical source impedance connected, whereas we are just grounding the input in this case. What I'd like to look at next then, after we've measured the noise floor, quite naturally that follows on then to the signal to noise ratio. So this is now where we do feed an input signal from a source into our system and we measure the output. We know what our input signal is, and this might be, for example, a 1 kilohertz, 1 volt RMS sine wave, and we look at the output and see the relationship between that signal we're feeding in compared to the noise floor, and that's our signal to noise ratio. So effectively wanted signal relative to the unwanted signal that might be these noise floors or any spurious signals that get added on due to distortion and so forth. Signal to noise ratio is typically denoted SNR and is typically expressed in decibels, so relative magnitude again. What we want for signal to noise ratio is, of course, a higher number the better, and that's also for dBs, so a higher dB number the better the signal to noise ratio is. Remember, we want a large gap or large spacing between our recorded signal, at least in their terminology here, versus the noise floor and any other spurious signals. Noise floors around 80, 90 plus decibels are pretty decent, but you'll see some pretty advanced systems with high dynamic ranges that go over 100, 110 dB dynamic range or signal to noise ratio. So what we do now is we attach back this 1/4 inch input jack and we connect that, as we saw at the beginning of the video, to the QA403 and pass in a sine wave of a known frequency and a known magnitude and let the QA40 software calculate the signal to noise ratio for us. So going back to the software, I still have 192 kHz sample rate. What I will be doing is changing my full scale input attenuator, for example, down to 12 or even 18 dBV attenuation, because we don't want to overload or overdrive the ADC inputs. FFT values we're keeping the same, but we will turn on the generator. So if I click on Gen 1 on the left on the generators, right click on it, we can set the frequency and we can set the amplitude in dBV. dBV was relative to 1 volt RMS, so I'll just start with 0, which is 1 volt RMS. Click OK, then I can click Run, and we wait, of course, a tiny bit to receive some measurements. Click to add measurements at the top, and I'll add on the left channel SNR dB, click OK, and we can see we've increased the noise floor because now we have this distortion here as well, due to maybe clipping in certain stages or general distortion artifacts, which of course will increase the noise floor. So anything that isn't this 1 volt RMS signal is effectively noise. So this is what this system is now computing. It's computing the magnitude of the 1 volt RMS signal, or our input 1 kilohertz signal, relative to everything else. And then it computes our signal to noise ratio to be just above 91 decibels, which is fairly okay. But we do see here we have some artifacts due to distortion. So for example, if we go to the generator, right click on that again, and maybe if we lower the magnitude of our input signal, so maybe to minus 10 dBV, wait a tiny bit for this to settle, we can see these distortion artifacts reduce, of course, but overall actually the signal to noise ratio has decreased quite a bit as well by about 10 dB. So you can see, depending on the input magnitude and of course sometimes also the input frequency, the absolute signal to noise ratio that is then computed will vary as well. What we can actually do, if we click stop and then go to the automated test at the top, we can plot, for example, various parameters versus frequency versus input levels and so on, which is very useful if you're trying to find, for example, sweet spots or where clipping occurs and so forth. We can of course also change maybe the window types. We change to a hand window. We might be able to get rid of this leakage we saw in the middle. And then if we change our generator again to 0 dBV and compare the signal to noise ratio result, you see we get slightly different values also depending on the type of FFT we use, the windowing function and so forth, and of course the input frequency and input voltage, so to speak. But this is one way of then measuring the signal to noise ratio. Another important measurement is of course that of the frequency response, and this is especially true for audio systems where we might want to have defined lower and upper frequency limits that are only in the audio band, for example 20 to 20 kilohertz, or for equalizers we might want to see how, for example, a control setting changes the boosting or cutting of a particular frequency band, how wide that band is and so on, and we can do that using a frequency response. Predominantly, we are interested in the graph of magnitude, so gain versus frequency, rather than phase versus frequency in this particular audio case. Nicely enough, the QA40 software does this for us. So if we go back to that, all we have to do is change the generator to frequency response, and this then generates a chirp signal, which we'll see in a second. We can right click, we can change the amplitude, various options of the chirp. We'll just leave this at 0 dBV, click run, and now we get the frequency response at the output. We have to change the scales a bit, otherwise it's a bit hard to see. So what we can see here is the frequency response for our I2S feed-through system. We have a relatively flat passband, and we do actually have some passband gain of about 2 dB. So it's not at 0 dB, which would effectively just be a 1 times gain. But from this, we can see we have a fairly flat passband. Keep in mind the scale divisions on the y-axis on the left-hand side. So only down 1 dB at about 20-25 Hertz on the left-hand side, and only down about 1 dB, maybe around 5 kilohertz-ish. We of course can find out our minus 3 dB frequencies, and that's from the passband. So if our passband is 2 dB, that means our minus 3 dB frequencies are at minus 1 dB, so 2 minus 3. Therefore, at minus 1 dB on the left-hand side, our lower cutoff is below 20 Hertz because our measurement range is only 20 to 20 kilohertz. And on the right, minus 3 dB point, looking at minus 1 dB, that is just under 10 kilohertz. And for an audio system, if this were a headphone amplifier, we would definitely want to increase the upper cutoff frequency. But since this is for guitar, this was specifically chosen to have a slightly narrower frequency band. So guitar, we might only have several kilohertz as our maximum. So 10 kilohertz seemed like a fairly suitable cutoff frequency. And it's good that we can use tools like this to verify our frequency response. Just out of interest, we can also see what this chirp looks like in the time domain on the left-hand side. If we go to display time, we can see our exponential chirp is a sinusoidal ramp in frequency, and that's passed to the input. And from that, we can reconstruct the frequency response looking at the output. Another measurement we might want to look at, and this is quite common in audio systems, is of course looking at the total harmonic distortion, or THD, as well as total harmonic distortion plus noise, or THD+N. Total harmonic distortion, effectively we're feeding in a stimulus input signal. This might be typically a 1 kilohertz sine wave at various input amplitudes and seeing what the output looks like. We'll hopefully, of course, see our fundamental frequency, but we'll also see harmonics. These might be even or odd harmonics, and those together form effectively the distortion properties of our system. THD has an equation, so we effectively square the sum of the unwanted, so to speak, harmonics in the system. So other than the fundamental, take the square root and divide by the amplitude of the fundamental at the output. And this forms the total harmonic distortion measurement. If we have more harmonics and if we have higher amplitude harmonics, that'll of course increase the total harmonic distortion. Sometimes this is wanted in a system. For example, in guitar amplifiers, we might want some sort of tube-like distortion where we might have certain types of harmonics and of certain levels that form the sound of our system. But for example, in a headphone amplifier, typically this harmonic distortion might be undesired. Another measurement is THD+N, so total harmonic distortion plus noise, and this doesn't just take the total harmonic distortion or the harmonics into account, but also adds in the noise values, and that's typically what you might see in datasheet specs. So for example, going to this headphone amplifier's website, we can see they also list various specifications, including THD, in this case without noise it seems at 1 kilohertz, with a certain load, for example. And they list this in percent, but this could also be listed in dBs or similar. We can also look at the codec datasheet, and that lists a baseline of the minimum THD+N levels at minus 95 dBb. So that's what we're at least minimally bounded by, of course, not taking into account all of the other circuitry that's in our design. Now going to the QA40 measurement software, the way we can measure THD is simply select the generator again. So Gen 1, I've selected an input attenuator, and we're currently passing in a 1 volt RMS signal. Let me just change my scales again, and we can see we're already seeing, without doing any measurements, these harmonics appear. If I click on one of these peaks, I can add these measurement cursors in, so I can see the dBV amplitude. If I click on this harmonic, this is an even harmonic, so it's just ×2 the input frequency. Then we have this harmonic, which is an odd harmonic, so it's ×3 this harmonic, and so on. So we could select all of these harmonics ourselves, sum the squares, square root, divide by the fundamental, and we could get our own measure of THD. But of course, we can let the tool do this for us. So we can click on Add Measurements, left channel, THD%, and I'll do THD dB, THD+N%, and THD+N dB. So these 4 measurements. And here we can see what values we get. And keep in mind, this is for a particular frequency at our input and for a particular input voltage or amplitude. This is also unloaded, so our system is only loaded by the probe and the input impedance of the QA403. So that might affect performance as well. So here we can see we're getting fairly reasonable performance for this kind of guitar effect amplifier, but compared to, for example, a rather high performance audio headphone amplifier, we're an order of magnitude off, so to speak. But if we, for example, change the generator and maybe change the amplitude to -6 dBV, leaving the frequency at 1 kHz, let's see how that changes the THD performance. And we can see that's actually slightly improved our THD performance by bringing down those levels. So there's of course some scope to play around. It depends on what, for example, your input magnitudes are allowed to be, where you get clipping, what your expected inputs are, and so on. And of course, you can change frequencies and so forth. If you'd like to do automated tests, you can also, of course, do that with THD. So we can go to the top left, automated tests. We can do total harmonic distortion versus frequency, which is a very common measurement. We can select a start level, a final level, increments, start frequency and stop frequency. And we can simply press OK, just leave the default settings. And this will now perform automated tests on our platform without us having to manually adjust frequencies, voltages, and so forth. You can also see the test running in the background, but it will continue once this test is done. Now that this automated test has finished, we can see the result of this plotted as a graph, which is fairly configurable. And for example, here you could plot frequency versus THD+N and then export those values or export that graph, for example. So this is how these automated tests can be very, very useful. And there's quite a few different ones on those. And I believe there might also be a scripting software for the QA403 so that you can create your own automated tests, which is a very cool feature. But as you can see, for the price, this is a very, very powerful tool with pretty cool specs as well. One more thing I'd like to bring up just briefly is the topic of A-weighting or generally weighting in audio measurements. And effectively, these are weighting curves. You can kind of think of them as customized frequency responses that are multiplied with whatever measurement you're doing. And this is typically applied to audio equipment. And you'll see sometimes on websites people stating noise floor with and without A-weighting or THD with and without A-weighting and so on. Because, for example, the A-weighting, which is in this Wikipedia graph, this blue curve on the right graph, you can see that attenuates more lower frequencies. Then we have this fairly narrow passband, and we're attenuating some of the higher frequencies up to 20 kHz. So this will actually in general improve mostly noise performance or noise measurements and results when applying A-weighting, because A-weighting actually accounts for how audio is perceived by the human ear, because we're less sensitive, for example, to low audio frequencies, and this is some sort of compensation to help with that. There are also other curves, A, B, C, and D, but the most common is A-weighting. And we can actually do that in the QA40 software. What I've done now, again, is I've disconnected the input, so I've just shorted the input to ground, and we're just doing a noise floor measurement as usual. So our value from before, again, was about 30 microvolts for I2S feed through. Again, you can choose various different window types. The effect on this isn't particularly large. But what we then can do is go to this weighting section. We can even enter user weightings where we could, for example, select A weighting. And what you'll see here is this characteristic low and somewhat high frequency roll off due to this weighting curve. And what we can also see is that actually our noise floor and RMS has improved quite a bit by about 4 to 5 microvolts down from about 30 microvolts. So nicely, the QA40 software also includes that. Of course, we can do the same thing for total harmonic distortion and noise and so forth. So for example, if I plug in my input again and then apply sinusoidal input voltage of 1 volt RMS at 1 kHz, and this is without A-weighting, we had our result as before at about -76 dB THD+N. If we add in A-weighting to this, we can see it's actually made our results slightly worse, because if we look at the graph of A-weighting, we can see low frequencies are attenuated and higher frequencies above maybe 5-6 kHz are attenuated, but actually we have a tiny bit of boost in this passband here, so from about 1 kilohertz to, let's say, 5 kilohertz, this blue curve. And in our particular scenario, this is exactly where our harmonics are. Effectively between 1 and about 10 kilohertz are our main problematic harmonics that contribute to the THD. This is why we actually get a slightly worse performance, because the low frequencies we didn't have harmonics other than noise. So we actually get a tiny bit of boost of the harmonics due to the A weighting. This is why we have a slightly worse result. So these are things to keep in mind, of course, but I just wanted to show you and illustrate this. So again, a huge thank you to the Quantasylum team for sending me one of these, and we'll be using this QA403 audio analyzer in quite a few future videos when we're analyzing maybe more advanced audio systems rather than these, let's call them somewhat crude guitar processing systems, because they don't have to have particularly impressive performances. And this tool is something we'll be using quite a bit for those as well, also to analyze filters, equalizers, and so forth. In any case, I hope this video was useful. I hope it showed you what measurements you might be able to perform with one of these devices and how to perform these measurements and certain things to look out for. Keep in mind this was fairly condensed, but hopefully a good introduction to doing these kinds of measurements and using this device. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest electronics, hardware design, PCB design videos, and more. Thanks again for watching, and I hope to see you in the next video. Bye-bye.